Hello, my name is Saptarshi Bhattacharya and I'm a research scientist at Pacific Northwest National Laboratory. And today I'm going to talk about our work on data-driven reliability assessment for marine renewable energy enabled island power systems. I want to acknowledge the efforts of my co-authors in this work, especially Vishwas Chalisazar, who's also my colleague at PNNL, and he is the first author of this work. So marine renewable energy has untapped potential as a generation option. And that holds true especially for island and coastal power systems, which often rely on a significant amount of energy import from the mainland grid in order to serve their demand. Now, how much are these marine renewable energy resources able to increase the operational reliability of these island and coastal power systems is a great question to ask, but one that if we want to answer by conventional reliability approaches, it would need a lot of system-specific information which might not always be available. Therefore, in this paper, we develop a data-driven method to characterize the resiliency benefit of including the MRE in the generation portfolio for an island power system. So the goal is to essentially develop quantitative understanding of MRE potential for offsetting that potential dependence on dispatchable fossil fuel based technologies. We do expect that the relatively higher predictability of marine renewable energy resources, especially wave and tidal resources, would enhance the operational renewability in some sense, and that is what we are going to investigate in the next few slides for a very specific case study of Nantucket, Massachusetts. Now we selected Nantucket as our case study because it has a very specific power systems configuration that we'll discuss in details in the upcoming slides. So as you can see from this slide, Nantucket is a very special power system as we mentioned earlier. So it primarily relies on two submarine cables for importing power from the mainland grid in order to serve most of its demand. Now Nantucket is also a summer peaking demand profile, largely driven by the tourist activities which also peaks during the summer. Now before we go into the methodology, we want to describe two terms that is critical in understanding what the data-driven methodology is for assessing reliability. First is generation buffer. Generation buffer is the difference between the maximum available generation and the actual generation which is being generated in order to cover for the demand plus the losses in the network at any given time. Demand gap, on the other hand, is the difference between the maximum possible demand or the peak demand in the system and the actual demand that is existing within the system at a given point of time. Now, define gamma k as the difference between the generation buffer and the demand gap. So gamma k gives defines the security condition of the power system at any given time. So higher gamma k would mean that you have enough adequate generation to cover for the demand gap, and therefore is always nicer to have from an operational standpoint. And we use this gamma k to define the risk metric, which is zeta of k, and you can understand that by this definition the zeta k values should be as low as possible in order to ensure lesser operational risk and more reliability. We should also point out that by this definition this risk metric can become greater than 1, especially when there are generation shortfalls and you do not have adequate generation to cover possible increments in demand within the system. So we analyzed our proposed methodology under different renewable energy generation portfolios for 8760 hours in one typical year, and we found that for Nantucket, Massachusetts, tidal energy was as effective as wind, which is a strong resource in Nantucket, Massachusetts, bringing down the operational risk of the power system, which is a great result to have. Wave is not as effective, however, that we found out. We also tried analyzing the case where you had contingencies, specifically single line contingencies, when one of the two cables is not available to provide you power throughout like one full day in one particular season, and we found that the tidal resources along with the wind resources, they were the most effective in managing the risk during those contingency periods as well. So to conclude, we believe that our findings in this paper show that MRE resources, especially tidal resources for Nantucket, Massachusetts, have strong potential in reducing operational risk for power system operation. For future work, we do want our study to be extended for other locations and other generation mix as well, and understand potentially newer value streams that marine renewable energy is bound to open up as they become more and more popular in context of power systems operation. Thank you. We hope you enjoyed our talk.